All right, welcome to the Explainer. Today we're going to crack open the universe's ultimate rulebook. We're talking about the fundamental laws that decide everything, why your coffee gets cold, how a battery works, even how stars are born. We are diving deep into thermodynamics. Okay, let's just stop and think about that for a second. When Albert Einstein says a theory is basically untouchable, you know we're dealing with something seriously fundamental. He was convinced these ideas were so core to reality that they just never be proven wrong. So, what is this powerful stuff all about? Well, at its heart, thermodynamics is kind of like a big detective story. It's really trying to solve one single central mystery. What makes something happen all by itself? What's the driving force behind any spontaneous change? To solve any mystery, a good detective has to define the crime scene first, right? And in thermodynamics, that means we have to draw a clear line between the thing we're looking at and, well, everything else. And it's a really simple but super powerful idea. You see, if we're studying a cup of hot coffee, the coffee itself is our system. The room, the air, everything around it, that's the surroundings. The key thing here is the boundary between them. Whether it's the physical wall of the cup or just an imaginary line, it's crucial for keeping track of what goes in and what comes out.
So think about it. That cup of coffee is letting steam, which is matter, and heat, which is energy, escape. That makes it an open system. A sealed bottle of water, well, that's a closed system. It can get warm or cold, but the water itself isn't going anywhere. And a perfect imaginary thermos, that's our isolated system, completely cut off from everything.
Okay, so with our crime scene defined, let's get to our first big clue in this quest for spontaneity. And this one's going to feel pretty familiar, pretty intuitive. Things just tend to roll downhill, right? They move from a state of higher energy to a lower one. Our first rule is a big one, the first law. And honestly, it's just the law of conservation of energy. You can't make energy out of thin air, and you can't destroy it. The change in a system's internal energy is simply all the heat you add to it plus all the work you do on it. Energy just gets moved around and changed from one form to another. So to track this energy change in the real world, we often use a handy value called enthalpy. It basically measures the heat that's released or absorbed, and this leads us to our first big theory, our first suspect, if you will. Maybe, just maybe, all spontaneous processes are the ones that release heat, the ones we call exothermic. And hey, the evidence looks really good for this idea. I mean, burning wood, a hot pan cooling off on the stove, these are all spontaneous and they all release energy. It feels like a slam dunk, right? Case closed. But is it really the whole story? Well, here comes the plot twist. Because it turns out our super neat energy-only explanation has a massive hole in it, and it's exposed by something we all see every single day. Seriously, just think about an ice cube melting in a warm room. For that to happen, it has to suck in energy from the air around it. Its enthalpy actually goes up, not down. So if our energy downhill rule was the only thing going on, ice cubes would never melt on their own. Something else has to be at play here. We are clearly missing a huge piece of the puzzle. And that missing piece has a name. It's called entropy. You can just think of it as the universe's natural love for messiness. A perfectly stacked deck of cards is super ordered, right? It has low entropy. But you shuffle it and it becomes random and disordered. It has high entropy. The universe is always on its own, shuffling the deck. Okay, let's really picture this. Imagine you've got a box with a wall right down the middle. On one side, you have one kind of gas. On the other side, a different kind. This is super neat, very organized, a low entropy setup. Okay, so what do you think happens if we just, poof, pull that wall out? Of course, the gases are going to mix all on their own, spreading out until they're totally jumbled up. You'll never, ever see them spontaneously unmix and go back to their separate sides. And that right there, that's the relentless one-way street of entropy. And this idea is so fundamental, it gives us our second law, which is even more powerful. It says that for any process to happen on its own, the total entropy, the total disorder of the entire universe has to go up. Okay, so now our detective story has two main suspects. We've got the drive to lower energy, which is enthalpy, and we've got the drive to create more disorder, which is entropy. They're in a constant tug of war. So how do we know who wins? How can we predict what's actually going to happen?
Well, this is where it all comes together. We need a judge to decide the winner, and that judge is an equation called Gibbs free energy. It takes both of our clues, the energy part, delta H, and the disorder part, delta S, and it puts them on the scales together. But here's the kicker. It multiplies that disorder factor by temperature, and that's huge. It means the hotter things get, the more that messiness, that entropy matters.
And the result is beautifully simple. You just look at the sign of the final number, the delta G. If it's negative, it's a go. The process is spontaneous. It will happen. If it's positive, nope, not going to happen on its own. And if it's zero, the system is perfectly balanced in a state of equilibrium.
This table here is basically our cheat sheet. It lays out every possible outcome in that tug of war. For instance, if a reaction releases heat and gets more disordered, that's a win-win. It's going to be spontaneous no matter the temperature. But now let's solve our ice cube mystery. Melting absorbs heat, so that's a positive delta H. But it creates a lot of disorder, right? Liquid water is way messier than a solid crystal, so that's a positive delta S. We look at our table, row 3, and it says it's only spontaneous at high temperatures. Why? Because that T in the equation cranks up the importance of disorder, making the whole thing negative. And that's exactly why ice melts in a warm room.
Okay, this is pretty cool, right? But what's the big deal? Why does this matter outside of a classroom? Well, it matters because with Gibbs free energy, we can basically predict the future of chemical systems with incredible accuracy.
See, there's this other equation that connects Gibbs free energy directly to something called the equilibrium constant, or K. And K is the magic number. It doesn't just tell us if a reaction will go, it tells us how far it will go. How much of our final product are we actually going to get when it's all said and done? You can imagine how important that is for all of modern chemistry and industry.
So what's the big takeaway here? The next time you see something as simple as an ice cube melting or a campfire burning, you'll know what's really happening under the hood. It's this incredible cosmic dance between energy and disorder, a fundamental tug of war, all decided by one elegant and powerful rule.
And that leaves us with one last really fascinating, mind-bending question to chew on. If the entire universe is constantly sliding towards more and more disorder, towards maximum messiness, then how is something as incredibly organized, as beautifully complex as life itself even possible?
That's a deep one for another day.
Thanks for joining this explainer.